Hey, welcome back. Let's talk about saw blades and milling machines. When you run a saw blade on a milling machine, just like with any other milling cutter, you want to know your, well, let's call it a relationship between the saw blade or the cutter and your work. So you know when it makes contact and how much you need to advance to put it in the right position. There are different techniques to achieve that. For example, you can run the saw blade at speed. Just approach your work until you hear a ka-chunk, 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 ka-chunk noise. If you ever have done this, you know the sound. And then you know that you're in contact with your workpiece. Or on the other end of the spectrum, you have a laser tool setter in your CNC machining center and a touch probe. The tool setter measures the offset of the saw blade to the spindle nose, and the probe, which has a given distance between the spindle nose and its probing tip, creates the relationship between the spindle nose and your work. And after doing all that, the machine knows where the saw blade is in relation to your workpiece that you touched off. Since my manual milling machine is more on the lower tech end of the spectrum, where we need a technique that's not relying on a laser tool setter here. But for the work I'm doing here, for this particular project, I need a very high accuracy touch off the saw blade to my workpiece. So I had to figure something out, and I think the technique I'm using is really bulletproof and very accurate. So let's have a closer look. This is the setup I'm going to use to demonstrate this technique. We're running the horizontal spindle on the milling machine because it's more convenient for the small production run that I'm doing. The same principle will work with the vertical spindle like on any regular Bridgeport. Also, I'm running the HSK quick change holder, so I can take my tooling out and change it between parts very quickly. This is a HSK 32 to ER25 collet chuck to hold my saw arbor here. I'm using the HSK interface in this case because I need to change back and forth between the saw blade and this tiny drill. There's a 0.5 stubby drill in a shrink fit holder. I need to change between those two tools with a high degree of precision, and the HSK interface allows me to do that. So I'm not losing any precision here doing this. Also, the offset in this direction doesn't change between changing it back and forth. So that's nice because it's a dual contact. It makes contact on the taper and on the face of the tool holder. So very accurate, very stiff system, despite the rather hilarious long stick out here. But that's fine. Run out here is brilliantly good. And same for the axial run out of the saw blade. It's less than 10 micron axial run out, which is fairly decent for a saw blade. The saw blade you're seeing here is 20 millimeter outer diameter and 0.15 millimeter thick. So a very thin and very fragile saw blade. That's also why the arbor is so oversized. It's a 16 millimeter shank for a 20 millimeter saw blade. So I get only a rim of 2 millimeter all the way around that's exposed. Carbide saw blades are surprisingly affordable. I think one of these blades is like 20 euros. These are from Carnache here in Germany. Very affordable. The part that you see up here, that's a brass alloy, is held in 3 jaws, and these are regular hard chuck jaws that I milled down. I cut this outer section here down, added a large chamfer, and I milled the ID of the jaws just like you would bore soft jaws on a regular lathe, just to give me a very precise, very safe grip on the small part. I can't show you the entire part, unfortunately, but this is good enough to show you the technique. I need to cut slits right through the center line of the part. So how do we get it aligned? And not like eyeball it to 0.1 millimeter, more like get it within 10 microns or better if we can. I saw this technique a long time ago on Instagram. I'm not 100% sure who showed it. And the idea was just to use a dial test indicator on the backside of the saw blade to tell you once you make contact with the work. How would this look in practice? What we need for this technique is an indicator stand and a dial test indicator. This happens to be a 0.01 millimeter dial test indicator, 10 micron. And now we bring the probe to the back side of the saw blade, roughly at the lowest point on the back side of the saw blade, not touching the teeth, but the body of the saw blade. What you see down here, the small sphere, this is the probe tip of the dial test indicator, right behind the saw blade, not making contact yet. Now I'm just moving the indicator ever so slightly until it makes contact with the saw blade. And I'm just giving it a little bit of preload, like this. And we don't even need to zero out the dial because we're just looking for the ever so slightest movement of the needle with this technique. So now we're all prepared to touch off on the workpiece. And what we created by adding the dial test indicator to the back side of the saw blade is we added a visual representation of the saw blade deflecting. This means when we touch the saw blade, we immediately get a needle movement. Means we can use the saw blade now to touch off on the work. Now it's just a matter of moving the saw blade against my workpiece until I get ever so slight movement of the needle here. Now we move in and you can see at the needle anytime that once we made contact that the needle moved a tiny bit. Let me back off again. There's the needle movement. This is when we make contact and we over travel by a few microns. So now we just move in a tiny bit until we get ever so slight needle movement. Like half the width of the needle, for example, and we zero out the DRO in this position. And you can over travel a few, like a little bit, like 10, 20, 30 micron will not damage the saw blade. It's flexible enough to withstand this. It's depending on the saw blade size of the stick out of the saw blade out of your arbor. The saw blade is way different, more fragile, therefore, than a large high-speed steel saw blade with small flanges for clamping it. So now we got zero on the back side. Now we want zero on the front of the workpiece too. So we move the saw blade to the front of it and we repeat the same deal again. We clear the dial test indicator. We clear the saw blade from the workpiece. We move the saw blade over. Now we need the probe of the dial test indicator, of course, on the other side of the saw blade. In this orientation you can see the position of the probe in relationship to the saw blade very well. We just need to add the preload to the dial test indicator now. So zero it out. Now we can touch off on the other side of the workpiece. But Stefan, you did forget about the runout of your part. Nope, I did not. We will spin the part 180 degrees around, since it's held in our rotary indexing head. And this will negate any runout in the part that's remaining from my adjustment process. So just going to do this. So we're going to do a 180 degree spin here. And now we can finally touch off on the other side. And this will give us the most accurate result in relation to the workpiece, no matter if there is a little bit of runout or not. Okay, there is my tiny bit of movement on the dial test indicator needle, right here. And let's look at the DRO. We're dealing with the y-axis here. And we get a reading of 7.15 millimeters. 7, that's the diameter of my workpiece. I know that because I turned it. And the diameter is within a few micron. And the 0.15 and the little bit of micron back here, that's the added thickness of the saw blade. I want to find the center now, so we take this axis and use the half button down here to split the number in half. All we need to do now is to clear the saw blade away from the work, drop the knee of the mill so we have C clearance, and crank the y-axis back until the saw blade is the center of the rotation of the indexing head. And that's when the DRO shows 0. Then we are at the true center of rotation of the indexing head because we did the 180 flip of the indexer before touching off on the second side. By using that technique, I cancel out any remaining runout error in the part and any out of roundness error. On average, this will give me the most centralized slot through the part because I'm doing several slots on these parts indexed by a few degrees. Would almost be a scam of a video if I had shown you the tiny drill bit in the beginning of the video but not show it cutting. But also this is a opportunity for me to tell you something about micro drilling attachments because that's one of the tools that belongs onto my list can go off a cliff. Micro drilling attachments are a way of adding a sensitive quill, either with a knurled ring that you pull out and move the drill with your finger, or with a tiny lever attachment, or in the case what Deckel sold, with a weighted power feed. In my opinion, they create more trouble than they are worth it. They have to be made extremely accurate. They add a ton of length in case of the Deckel sensitive drilling attachment, and they're kind of unnecessary. One might say, but Stefan, I don't feel the drill cutting when I don't use the sensitive drilling attachment. Well, that's true, but even with the sensitive drilling attachment, you will have a hard time feeling anything with a 0.3 or 0.5 millimeter drill. So in my opinion, it's better to look at what the drill does instead of trying to feel it. Look at how the chips come out the flutes and make a judgment according to that to your feed. CNC machines don't feel the drill either. They have a programmed feed rate and they're drilling tiny holes all day long. So I'm drilling here 0.5 millimeters and I have 20 parts with 8 holes each, and I'm not worried about the drill at all. Runout of the drill is way more important in this case than having a sensitive feed attachment. I'm running a very short fluted Zecha drill in a shrink fit holder, so runout is not an issue here. And due to the stubby length of it, I don't need to spot drill for it. And perfectly fine just to hand crank it in. For doing this, I am just indexing the part to the next position and drill next hole. And by feeding the entire y-axis of the machine, it's a very, very solid, very free of play movement. And I have the benefit of using the DRO for both. It shows me both my actual feed rate that I'm hand cranking the axis in millimeters per minute, which is the standard unit for feed rates in milling. And also I can have a very precise measurement of my depth. So only benefits here. While doing these parts, you sit there and you think a lot and you make all your cuts and can't get in a meditative state. And while doing that, I had an idea for a different technique how to center a saw blade. Kind of obvious if you think about it. When the part is sitting on a rotary axis, like in my case, you can just use an indicator on the rotary axis to center the saw blade relative to the rotary axis. So in some cases this might be a very, very viable option. I can show you. I just have a dial test indicator with a small stand here and the tip pointing upwards. By the way, I sometimes read in the comments that this will lead to an error in your measurement. That's wrong, because it's not 90 degrees to the indicator. The cosine error of a dial test indicator happens between the angle of the stylus relative to the surface you're probing against, not relative to the body of the indicator. So this is perfectly fine and will not create a cosine error. By the way, cosine error first gets relevant at maybe 15 to 20 degrees between your measured surface and the stylus angle. And then there is a correction factor that you will find in the manual of your dial test indicator, hopefully. The idea with this technique is to just move the dial test indicator so it touches the saw blade. And then you just sweep the saw blade like this. Find your low spot. You zero out the dial. And you drop down. You spin 180 degrees. I have to be a bit careful to not hit the tripod again. You spin 180 degrees and you get your probe in contact again. And you sweep to 0. And you split the difference as usual, and then your saw blade is on center line. Just as a bonus idea. This will not work, of course, if the part is just held rigidly on a machine table in a vise. But if you're dealing with a rotary axis, very viable option. That's, by the way, also a technique to center slotting tools on a vertical slotting machine that has a rotary table, or on a tool room mill with a slotting head and indexing head, to center the slotting tool extremely precise to the bore and not rely on doing scratch passes with the slotting tool in the bore. Here in close-up, I have the indicator here on a larger radius spinning, and I bring the saw blade into contact with the probe until I get a little bit of needle movement down here. Then I sweep with the rotary axis for the high spot, or in this case low spot. It's here. And then I crank the axis to a convenient number on the dial test indicator, and I zero out the axis in this position. Drop the C-axis, move the whole deal approximately 180 degrees around, like this. Then I crank the Y-axis back into this position, and I bring the probe into contact again. And I'm sweeping for the low spot. That's here, and I crank to the same zero marking on the dial test indicator again. A little bit hard to read for you on the camera, and even harder for me in real life, because the camera is in the way. But I can just look over. Okay, that's 0. Now I have an arbitrary number in the y-axis, and I take that number, split it in half, crank the axis to 0, and now I'm exactly on center line with the axis of the indexing head. Completely not influenced by any run out in a part or work holding or something else. It's only the error motion in the spindle of the indexer left, and of course the total allowable error in the dial test indicator, which is a few microns in most cases. While we're here, I can also show you another application for this technique over on the lathe. If you need to space a snap ring groove or another feature, or you need to part off a piece to a very precise length, I would first of all question the design intent, and then secondly use this technique with very flimsy part-off tools like this 1.2 millimeter thick parting insert. It works very well. Just put the dial test indicator very close to the tip and approach the face of the work, and you will very easily get a reaction on the needle once you touch the workpiece. And if you, for normal tolerance work, it's perfectly fine if you just go by a little bit of needle movement and then ignore how much that is. It's fine usually. If you really want to be picky, you could do like 10 micron over travel, and then take that into account when moving the tool into final position. Also, don't forget to remove the dial test indicator before you take your cut. Oh yeah, this technique is rather versatile and works in a lot of use cases quite nicely. Also works with something like this flimsy high-speed steel blade. Even better because high-speed steel is 3 times less stiff than carbide. So you can even over travel it to a very funny amount. This is, in my opinion, a good alternative to, well, there are different techniques that I like to use. My most used one is just to use 7x magnification and approach the face of the work with magnification, and you will see very precisely once you're at your position. But in some cases that's not viable, or your eyesight might get worse over time. We're all decaying and falling apart. So having dial test indicator is usually very helpful. So I hope you enjoyed this little short, in reality painful long toolroom tip, but I think it's worth to go into detail on those techniques and not just glancing over the basic principle. You can do a lot with just an indicator on a milling machine or a lathe. So I hope you learned something. I hope you enjoyed. Thank you all for watching. Thanks for the support, and I'll be back.